introduce. Okay, I am very glad to introduce Feng Xu from the University of California, Riverside. Feng Xu is a truly incredible mathematician, extremely strong, and I had the fortune to collaborate with him and so to understand directly how strong he is, and I greatly took benefit from that. And Feng was outstanding since the beginning, because he moved from China to Berkeley when he was at the PhD, and he was very young. I don't remember, but I think less than 20 or something. And then he took a PhD with Von Jones, and already soon at that time he started to work with conformal field theory, and with a series of deep and extremely involved results. And after that, he continues his career. More recently, he's working in entropy. And I think this is a very nice occasion to listen about his more recent results. And so please go ahead, Feng.
Thank you, Roberto, for the kind introduction. And I'd like to thank the organizers for inviting me. So I will be talking about a topic which I have talked about recently. So I apologize to those of you who have heard my recent talks before, but I hope to emphasize on maybe slightly different aspects in today's talk. So this is based on some recent work, sometimes joined with Roberto and other people. So let me start with the outline of the talk. So I will spend quite some time discussing about the motivation and the main results. And then, then I will give a gentle introduction to entropy and the relative entropy. And then, so I will set up the stage so I can describe the main results precisely. So these are the gradient nets and subnets. And then, so I have quite a few bullet points, but don't worry about it. Some of these are very short, so I hope to be able to get to the end in today's talk. All right, so let's start with motivation and main results. So, so in the last few years, there has been enormous amount of work by physicists concerning the entanglement entropy in quantum field theory. So physicists have very good motivations. My interest in the subject is mainly on the basic mathematical questions. So I want to understand the mathematical aspects of the story. So for instance, one such mathematical question is the following. So most of the entropies computed in the physical literature are infinite, okay? So in some sense, the singularity structures, and from a mathematical point of view, the cutoff independent quantities of most interest, okay? Often the mutual information is argued to be finite based on heuristic physical arguments. And then one can, from a mathematical point of view, if that mutual information is, it seems to be more fundamental, for the reasons I'll explain in the next few minutes, one can actually derive the singularities of the entropies from the mutual information by taking the singular limits of this mutual information. Okay, but I should say that such mutual information, which is well defined as a special case of Araki's relative entropy, one needs to prove that it is indeed finite. Okay, so this is, a few years ago, what we think the basic mathematical questions which one has to answer. Okay, so we began to address some of these fundamental mathematical questions. Okay, so here's so maybe I should say a few words about previous results before work. So for instance, Hollins and Sanders and some others have also considered this. I should say that our work is strongly motivated by Ed Witten's questions, in particular, his questions to make physicist entropy computations rigorous. Okay. Now, in this talk, I'm going to focus on chiral CFT in 2 dimensions. The results in that context are most explicit and also have interesting connections to subfactor theory, if you know what that is, but otherwise that's fine. I should say that some of the results do not depend on the conformal symmetries and apply to more general quantum theory. So I'd like to describe some of the main results here. So the main results, the first result is the exact computation of the mutual information through the relative entropy as defined by Araki for free fermions. Okay, so I'll define what these things are in the next few transparencies. So let me continue with this. Okay, so the proof of this result is actually quite intricate, and we have to use various kinds of tools. So, for instance, one of them is the usual convexity discovered by Loop, and also the theory of singular integrals. Okay, so let me describe the results. So the results is in the free chiral net associated with R fermions is the following. So if you take 2 intervals which are disjoint from each other, and you consider the mutual information associated with these 2 intervals. So what this means is that you take the relative entropy for the vacuum state and the tensor product of vacuum states restricted to A and B. That relative entropy is given by this formula. Okay, I've defined this precisely later on. So not only we show this is finite, there is actually precise formula. So it's minus R over 6 times logarithm of eta. Okay, well, eta is the cross ratio in this case is between 0 and 1. So log of eta is negative. So we have a positive quantity right here. Okay, so that's one of the main results. Okay, so when you look at these results, of course, in physics paper, you will see this factor of 6 coming from the replica trick, and so physicists have a very impressive way of getting the right number but sometimes for not very precise reasons. So here we have everything is well established. Okay, but anyway, so you might think that this is well, it's nice that you have exact result, but what's the how do you actually use this? Well, there are many applications. So from this computation in the simple free fermion case, and the fact that relative entropy has this monotonicity property, I will also describe this later. It follows that if you have a chiral CFD, which can be embedded into free fermions, then automatically follows that the relative entropy in the previous page all follows to be finite because they're smaller. Okay, so in this way, we verify many of the claims by Cassini and his collaborators. So this includes, for instance, large family. In fact, all the known examples of chiral CFD. Okay, so by various tricks, you can embed, for instance, all the WZW models into chiral free fermions or tensor product chiral free fermions. Okay, so we'll verify many of the claims. As also a theorem connects relative entropy index of subvectors in an interesting and sort of unexpected way. Okay, so let me make a comment on this. This connection is different, okay, but related to Pipson-Popper result that connects Klein's total entropy to index. Okay, so so this, the original Pipson-Popper result is in the context of type 2-1 factors, and Roboto also generalized that to type 3 case to any von Neumann algebra, any factor, in fact. But our connection here, in fact, I will probably discuss this at the end of my talk, is actually different. Okay, but our results are obtained on in a framework where there are more structures. Okay, I should say that there is also one bit of surprise it's usually postulated that mutual information of pure states, such as vacuum states for complementary regions, should be the same. But in the chiral case, this is not true, and the violation is measured by the global dimension or the mu index of the net. I will also mention this at the end of my talk. Okay, so yeah, so this violation, which in fact, if you look at it carefully, it's really due to the purely to the type 3 nature of the observable algebras coming from quantum field theory. Okay, so the precise violation is actually proportional to the logarithm of the global index, which also turns out to be what some people call the topological entanglement entropy. Okay, so I will describe a formula at the end of the talk. So this is the first section where I describe about motivation and main results. Okay. Yes, please feel free to interrupt me if you have any questions. I cannot look at the chat or even see the people on my screen, so it feels like I'm talking to the screen myself. So yes, please feel free to ask questions. Okay, so let's move on to the next one. So I have used some words like entropy and relative entropy in description of in my previous description of the main results. So now I like to define those things. So let's start with entropy and relative entropy. So the von Neumann entropy is the quantity associated with a density matrix on the Hilbert space. Okay, so this is the formula. You got minus trace rho log rho here. So rho is a density matrix, rho is greater equal to 0, less equal to 1. So this is a positive quantity. So von Neumann entropy can be viewed as a measure of the lack of information about the state. So for instance, I have already mentioned that it's always greater equal to 0. For pure state, it's easy to see that this is always equal to 0. Okay, and if your Hilbert space is finite dimensional, the von Neumann entropy attains its maximum value when rho is 1, let's say h is dimension n, then the maximum value is logarithm of n. That's when the density matrix is 1 over n times identity matrix. Okay, so it attains its maximum value when the state is it's further away from, it's most away from pure state. Okay. Anyway, so one thing you can see about von Neumann entropy here is that because of this logarithm term, it's nonlinear. Okay, and in general, it's not easy to compute this even in a finite dimensional case. Okay, in fact, if you look at the literature, there are lots of computation of this of the entropy of a state. For instance, a statistical mechanics model on finite lattices, in which case the Hilbert space is finite dimensional. Of course, it's fine, even though it's finite dimensional, it has large dimension, and you want to compute certain entropy here, and the mathematics behind this is surprisingly intricate. So, for instance, you will see things like computation of the determinant of tuplets matrices and so forth. Okay, and then occasionally people will also be interested in taking the size of the finite lattice to 0 to approximate the infinite dimensional case. Okay, so there is a large literature on computation of this. Okay, now a related notion is that a relative entropy is defined for 2 density matrices in the following way. So this is a formula, like instead of 1 density matrix, I have 2 density matrices, and this is the formula. Okay, so a little bit of computation using convexity, one can show that this is always non-negative. It can be infinite, and is equal to 0 even only if rho is equal to rho prime. Okay, so this relative entropy, it's like sort of some kind of distance, measuring the distance between 2 states. Okay, but of course this is not really a metric because it's not symmetric in rho and rho prime. Sometimes people just take the sum of this S rho rho prime and S rho prime rho and divided by half, and think of that as a metric. Okay. So that's the von entropy and relative entropy in the case when we have a density matrix on a Hilbert space. So the algebra, the underlying algebra is B of H. That's a type 1 factor. Okay. Now, amazingly, turns out that this notion of relative entropy, in fact, is completely general. You can define this for arbitrary type of von algebra, not just for B of H. This was found by Araki, and is formulated using modular theory. Okay, so this is what I've written down here is precise definition using relatively modular operator. Yeah, so I would not say much about this because we're not going to use this. The reason I'm writing down here is because, just to show you that there's precise formulation of relative entropy now for any type of von algebra. So this is the definition given by Araki. So it's the expectation value of the logarithm of this relative modular operator. So this is sometimes known as modular Hamiltonian. Okay. So there's a precise definition, but we're actually going to rewrite this a bit in a slightly different way without using modular operator later on. Okay. But what's the relation between this definition and the type 1 definition I defined earlier? The phenomenon is when you have density matrices, well, it's supposed to be a generalization. So not surprisingly, if you go back to the type 1 phenomenon algebra, the states will correspond to density matrices. You unpack what's contained in the definition of Araki's relative entropy. Of course, you will recover the definition I mentioned before. That's when we have two density matrices. Okay. Now, there's another example. This is a familiar example for people in quantum information theory. If you consider bipartite system, where the Hilbert space is the tensor product, the observable algebra is the tensor product of these two factors here. A normal state will correspond to density matrix. And then when define rho A as this density matrix rho AB, but trace over HB. Okay, this is called the reduced density matrix. Okay, this defines a state on one of the factors because you trace over the other factor. Okay, and similarly, you can define this for the system B. Now, the mutual information I mentioned earlier in this context is given by this formula. So this is the relative entropy between rho AB, the original state defined as the tensor product system, and this tensor product states, rho A tensor with rho B. Okay, if you compute this relative entropy, this is called the mutual information, is given by this formula. Okay, so this is formula related to relative entropy to the phenomenon entropy. Okay. Now for tripartite system, that's when you have three tensor product of three Hilbert space, and then if you apply this formalism and using a property which I describe in a minute, it's called monotonicity of relative entropy, you will immediately recover this inequality. Okay, so this is inequality about 1, 2, 3, 4 phenomenon entropies associated with different subsystems in this tripartite system. Okay, so this is what's called the strong subadditivity. Originally, this was proved by Loop and Roskay for I think maybe in the late 50s or maybe early 60s, but I don't remember exact date. The proof is quite intricate, but this, as we see, follows rather easily from the monotonicity of the relative entropy. Okay. All right, so it shows that these properties of relative entropies are very important. If you cast this in different systems, sometimes you get surprises like the strong subadditivity here. Okay, so yeah, that's a discussion about how Araki's relative entropy is specialized to the usual definition for relative entropy in the type 1 case, and sometimes the monotonicity leads to interesting inequalities among entropies. Okay, so let me go to Kosaki's formula. So this is a formula without using modular operators. So it's a formula for Araki's relative entropy, but using states omega prime directly. Okay, it's a variational formula. It's not very pleasant looking formula, but I hope to convince you that one can learn quite a few things from this formula. Okay, so this is Araki's relative entropy. Now Kosaki's formula says the following: is the soup of the following expression. There are two soups here, so let me explain the items here. So m is a positive integer, and the second soup is xt plus yt equal to 1. So xt is a step function valued in phenomenon algebra M. Okay, so it's a map which is defined, let's say, finite number of intervals, and on each interval xt takes a constant value in the phenomenon algebra M. Okay, in other words, the range of xt is a collection of it's a finite set of elements in this phenomenon algebra M. Okay, and here is the first term is logarithm of M. The second term here, sorry, I don't know. The second term here is an integral from M inverse to infinity, and we evaluate the state on xt star xt and omega prime on yt star. Notice the star is in different position. You know, this is for people who are familiar with modular theory. This is, you know, the fact that states evaluated in star x and x star is different because we usually in the type 3 situation. That's what made modular theory interesting. Okay, and this limit here. So eventually we're going to let m go to infinity. So this is like a 0 to infinity, but you know there's singularities of 0. So this is a bit of regulation of the singularity at 0.0. Okay. Now, of course, in practice, to evaluate entropy in this, it's hard. You have two soups, but you know, if you have a supercomputer and you have a good control of the elements in the phenomenon algebra M, this is probably okay. But I don't think anybody has computed entropy using this formula. But this formula can be used to derive many interesting properties. Okay. So here I'd like to describe two results. Okay, so the first one is the monotonicity property of relative entropy. I have said a couple of times already. So if I take omega 1 phi, be two normal states on the phenomenon algebra M, and I take omega 1 phi 1, the restrictions of these two normal states, the phenomenon sub-algebra. Okay, then it follows that the relative entropy is going to decrease. Okay, let's see how it follows from this formula. We have two soups. Let's ignore the soups here. Remember this xt and the yt has step functions. So this integral here is really a finite sum of these two states, omega and omega prime, evaluated on the elements in the phenomenon algebra M, right? Now let's see what happens if we compute relative entropy when restricted to the sub-algebra. That means we still taking two soups here, but evaluating on a smaller algebra. In other words, you're taking the soup over a smaller set. Okay, so that's why it's decreasing. Okay, so that's, you know, this definition, this property of monotonicity is built in from this variational formula of Kosaki. Okay, there's another example. If you take increasing net of phenomenon sub-algebras with the property that the union would generate M, then the relative entropy restricted to smaller, to this increasing net of smaller algebras would converge to the relative entropy defined on M. Okay, this is also obvious from this definition, because first of all, we know this is increasing sequence. We want to show it converges to this one. So we want to show that it can get arbitrarily close to this particular value, right? But let's see what S omega 1, S omega 2 is in this formula. Is the soup over some expression involving finite number of elements, the evaluation of this omega prime and finite number of elements in phenomenon algebra M, right? But by assumption, this finite number of elements in the phenomenon algebra M can be approximated to arbitrary precision, in terms of evaluation of the states by elements in MI, right? When this MI, when this index, let's say, is sufficiently large, MI can approximate elements in M in a suitable sense. So therefore, this can get arbitrarily close to S omega 1, S omega 2 here, okay? So this is the martingale property, which is very important. Frequently, in fact, in proof, one of the main results, we use this property. We see what a formula looks like in fine dimensional algebras, and then we want to show that, using that property, the limit of that formula gives the relative entropy we want to compute, okay? So in other words, in Kosaki's variational formula, many of the fundamental properties of relative entropies are built in, okay? All right. I should say that there are some formulas, there's some properties of relative entropies does not follow directly. So here's one of them, but I probably will not say much about this, okay? Okay. All right. Yeah, so maybe one comment, I think most of you already know, for type 3, factors, the non-M entropy is always infinite, but the relative entropy is finite, okay? So that's why we think that the relative entropy is more fundamental, okay? In fact, the singularities of the phenomenon entropy can be seen from the mutual information if you take the singular limits. Okay, I'll probably have such an example later on. All right, so so hopefully I have given you some ideas about what entropy and the relative entropy is like. But one of the results I mentioned earlier, is about relative entropy in the case of free fermion. Okay, so we need a formulation of that story, but this is the more general context of nets and subnets. So I think most of you in the audience are familiar with these concepts. So I'm going to go through this rather quickly. Just say a few words along the way. So, so this is a formulation of quantum field theory in terms of phenomenon algebras. So in the chiral case, in the two-dimensional chiral case, we're going to associate. So because two-dimensional, of course, but in chiral we only consider half of it. So space-time is really the circle is conformal. So space-time is a real line. When you compactify it, it's a circle. So we're going to associate to each interval of the circle the algebra of observables. And so this assignment, of course, this is the DHR analysis adapted to this setting, the map associated to the interval of the circle, the algebra of observables localized on that interval, and is supposed to satisfy various conditions. Most of the conditions are obvious. So for instance, this is all the conditions. The isotonic condition simply says that the algebra of observables localized on the smaller interval is naturally contained in the algebra of observables localized on the bigger interval. And we also require some covariance condition. For conformal theory, this covariance condition is upgraded to diffeomorphism covariance, positive energy, gradient locality, because we're going to consider fermions in a minute. So for fermions, it's going to be Z2 commute or anti-commute, okay? And the existence of vacuum, uniqueness of vacuum, and so forth. Conformal net, this is what I said earlier, the Mobius covariance has to be upgraded to diffeomorphism covariance. Okay. All right. So there's some standard properties of such covariant net. So, for instance, if you look at the modular operator associated with an interval, the modular operator is geometric. Okay, it's the Lorentz boost. Okay, this is one of the key properties. Okay, so let me just quickly go through this. Yeah, one of the reasons, of course, we are interested in such theories because unlike higher dimensions, there are lots of interesting examples. So for instance, a large class is provided by the chiral conformal field theory associated with a simply connected compact Lie group and its variations. So this so-called West-Zumino-Witten model. Okay, these are building blocks of rational CFTs. Right, so yeah, so one of the nice features about such formulation is that in this context, the composition of two superselection sectors, same as Kahn's fusion, is manifestly unitary associative, and this makes a lot of proofs of many important results in this context easier in that aspect. And here I also describe what's called orbifold in this construction, but I don't think we will use this that much, so I'm going to skip this. And of course, I should also mention the complete rationality introduced by Robato, Kawagashi, Robato, and Muger. And so this is, so maybe I will not say much about this. Yeah, okay. And the split property. Okay, the split property has recently played a very important role in physics. Physicists seem to be very interested in this concept, and yeah, I don't think I will. Yeah, so one thing about split property is that for the type 3 factors we have here, there's always increasing family of sort of canonically defined type 1 factors which approximate the fundamental algebra in a certain sense. Okay? This sort of, in my opinion, sort of explains why many of the formal manipulations by physicists seems to give the right result. Okay, for instance, in physics literature, you frequently see the computation of entropy just starting with a density matrix. They use what's called a replica trick, and they frequently arrive at correct results. Okay. I think that's because in some sense, even though the observed algebra is type 3, there's actual approximation. And if you know the quantity you want to compute in the limit has nice property like the relative entropy, then I'm fine, because the martingale property actually approximate. Okay, so right. Right, so this is, yeah, I think this is what I just said. Okay. So this is the one reason that many formal computations in physical literature, which only applies to type 3 factors under certain conditions, turned out to be true also for local algebra, which is always type 3. Okay. So, like I said, you need to have the control on the quantity you want to compute. So relative entropy happens to be such a case. I should say that the entropy itself doesn't have that property. Okay, it doesn't have the martingale property. Okay. Okay, so right, and also mentioned topological entanglement entropy before, but for those of you who know what's mu index, the logarithm mu a, it's what this physicist called the topological entanglement entropy. Okay, so this is a little bit of orbifold theory. I would not say much about this. Let's see. Okay, so now I want to just go ahead and at least show you, what our main results are about in the free fermion case. So, so this is the usual formulation of free fermions, the chiral for fermions in the language I just described. And so what is the observable algebra? Okay, so it's generated by these operators, these so-called Clifford operators. 6 psi, where psi is an element localized, the L2 element, which is localized on this interval I. Okay, R is the number of free fermions here. Okay, that's the free fermion net. It has the interesting property that the global index is equal to 1. Okay, and what's the definition of mutual information in this context? Well, we have to describe the state and the algebra. Okay, so first of all, we take 2 intervals, I1, I2 disjoint. What is this? What is the algebra? The algebra is the tensor product of observable algebras, the free fermion net localized on I1, tensor product with the free fermion localized on I2. Okay, remember these are generated by Clifford operators with support on I1. The subscript 2 here just indicate that in the free fermion case, the tensor product is the Z2 graded tensor product. Okay, so this is the algebra. What are the states? Well, omega is the vacuum state. That's clear. Okay, for the net. And omega 1 is the vacuum state restricted to the first factor. Omega 2 is the vacuum state restricted to the second factor. So here's the relative entropy between 2 states. And these 2 states on this algebra. Okay, so that's the mutual information. And our main result is the computation. The main results I mentioned before is the computation of this quantity. Okay. And the computation of this quantity is surprisingly intricate. And we use all the properties about this relative entropy, also specialized the free fermions, because after all, this is a free theory, right? The quantum field theory in this case is built on the Fock space. So many of the things can be reduced to the pre-quantized case, right? So that's how we are able to compute this relative entropy. Okay, so let's see. Maybe I'll just say a few words about this. In the interest of time, I will not describe all the details. So these are, in fact, I've written down many of the details of this computation. So the computation roughly goes like this. We start with the mutual information computation in a fine dimensional case, where we know that there is this formula, and then we take a limit, okay? Knowing that relative entropy has a martingale property. So if we know the formula for the fine dimensional case, so this is the formula expressing the mutual information in the fine dimensional case in terms of some finite matrices, okay? This P is a projection. This is a projection onto the finite dimensional subspace, and P converges to identity strongly. We want to show that from this, we can get a formula for the Araki's relative entropy in the net, in the continuum limit, okay? And this is not easy thing to do, right? We have some operator. We know this operator converges strongly to another operator. We want to show that the trace also converges to the trace of this operator. To prove tracial convergence is a much harder problem, okay? But fortunately, for us, this is not just any trace of any operator, right? This is related to entropy. Entropy has lots of convexity properties. So these are the properties which we explore. And these are actually the properties which we ensure that even though this converges strongly to the operator, the actual, in terms of trace, it also converges, okay? So the next few transparencies shows how we actually do this. We use operator convexity. We use Loop's concavity theorem. Loop's concavity theory is a generalization of convexity in this context. It's joint convexity in 2 matrices now. So we explore that, and so And then, we want to actually prove this inequality is equality, so that takes some efforts. And in the end, we'll be able to do this. So now we're reduced to compute the trace of some particular operator. Okay. So compute the trace of operator, we need to find the resolvent of this operator. And it just so happens that in this particular case, it's related to the Riemann-Hilbert problem. And you find the resolvent of this operator. This operator I didn't mention before. It's it's what's called covariance operator. Is expressed in terms of singular integral. Okay, so surprisingly, it's related to the resolvent problem is related to Riemann-Hilbert problem, and usually for the Riemann-Hilbert problem, it's very hard to find exact solution. Frequently, people will be able to get some results from about asymptotics. Okay? But in free fermion case, it's relatively simple. There's actually exact formula for the resolvent Okay, so this is the resolvent formula in that case. Okay, it's not the easiest looking resolvent you might hope, but the unusual thing here is that there is an explicit formula, and so we can compute the trace. Okay, so that's how we end up actually get the results. So let me just So the computation of this is actually very interesting. So for instance, you wonder how this number 6 come from. It comes from Euler's famous solution to Bazel's problem. From a physicist's point of view, this of course is also related to the central charge. In this case, is half. So physics formula says it should be central charge divided by 3. Okay. But that formula was obtained with a cutoff epsilon and with replica trick. Okay, and I think it's still interesting to give the variation of that formula, but that seems to be out of reach right now. But at least in this case, this is how we get this formula. Okay, this factor of 6 comes from this computation here. Okay. All right, so here is the theorem which actually generalizes what I stated earlier. So this is the theorem not just for 2 intervals, but for n intervals. Okay, and this is the relative entropy formula or the mutual information formula for the states. Okay, for free fermion net, this is the formula, and you can see that these terms here, the loss of cross ratio involved because of conformal covariance. The vacuum states are PSL2R invariant, so that's why you see lots of cross ratios here. When you specialize to intervals, this is exactly the formula I mentioned as one of the main results at the beginning of my talk. Okay. All right. So let's see. Yeah. So I have about 15 minutes left. So I'm going to just go over some of the consequences of this exact formula, and this is obtained by using the results for free fermions and also the results coming from subvector theory. Okay, so let's. So this is about the formal properties of the nets of the free fermion and their subnets. Right. So by formal properties, I mean this is motivated by the work of Cassini and his collaborators. So I should say that maybe I draw attention to this particular one. Okay. So if you look at the mutual information formula, you see that it can be expressed in terms. I mean, in the type 1 case, it can be expressed in terms of von Neumann entropy. Okay, so the idea is to see if similar formula or similar looking formula is also true for the mutual information, even for type 3 factors. In the case when we evaluate this in the continuum limit in some sense. Okay, And the answer is almost yes. So maybe I will see. Right, so there's some formal properties. You can define what's called a formal or regularized phenomenon entropy. At least in the free fermion case, you see something like this. Verify many of the formal properties as if, you're in the type 1 situation. Okay, so let me say a few words about that. Okay. Okay, so let's see. Okay, so let me see where. Okay, so maybe I will just say a few words. So this is like a regularized phenomenon entropy. Okay, here. By this I mean, if you in the free fermion case, if you take this definition, you will see that the mutual information behaves just like the formula just behaves like in the type 1 situation. But this is complicated looking formula. Well, it's not too complicated. I mean, if you take two intervals here, this is just logarithm of the length of the interval. Okay. But we know that the value here is not always positive. So this is not a phenomenon entropy. Okay. With this quantity, if, the mutual information behaves as if they're in the type 1 case, but this, what we call the regularized entropy, phenomenon entropy, is not the really entropy because it actually can take negative values. In fact, when the length is small, it goes to negative infinity. Okay. But at least you see some formal properties there. And I think this is still, this is a very interesting thing to study. And in fact, at the end, I'll say a few results in that direction. Okay. All right, so so I have said before about the singularities, right? So mutual information or relative entropy is a more fundamental, I mean, from a mathematical point of view, it's the only well-defined quantity in the continuum limit, right? So how do we see the singularity structures? Okay. Well, we can just take the singular limits. So here's an example of such a singular limit. I have two intervals B and C. So the endpoints is A1, A2 epsilon. So A2 epsilon is very close to A2 here. The distance between these two endpoints is epsilon, okay? So when epsilon goes to 0, one of the endpoints here is going to touch one of the endpoints in this interval C here. This is what I mean by taking the singular limits. I know the mutual information for these two disjoint interval is well defined. I want to study its limiting property as epsilon goes to 0. That's what I mean by structural singularities. And it turns out this structure of singularities is surprisingly rich. Okay, so I want to show you one such result. Okay, so here's the result I want to discuss. So here's two intervals. I will have one of the endpoints getting closer to the other endpoints. Okay, and this FBC here is just the mutual information for B and C, just like in the free fermion case. I'm stating the results in a more general context using a little bit of subvector theory there. Okay, so here's the result. We got some constant, and there's a logarithm of epsilon term. This logarithm of divergence is expected. And then let's look at this term here. There's a -12 logarithm mu b here. Okay, mu b is the global index of this net. So this is an index-like quantity, okay, coming from taking the limit. Okay, and there's an O epsilon term here. Okay, so the singularity of this mutual information reveals some of the underlying structure, okay, of, in this case, the conformal net. And the mu index, of course, is one of the most interesting quantities, and is recovered in the singularity structure of this relative mutual information, which I find quite surprising. Okay, so you see this sort of indirect connection between the relative entropy and some index theory here. okay? But of course, this is asymptotic result. And at the end of my talk, I will describe identity instead of asymptotic results, okay? All right, so, yeah, so a brief comment here, this, yeah, so we'll verify some of the results in the physical literature. And right, so here's, let's see how much time we have here. So maybe I will skip the failure of duality. Right, and I will discuss maybe spend a few more minutes on the last two topics here. Okay, so on the duality. Okay, so we have a paper about the relative entropy in the global index, and this is the paper which is sort of motivated by these duality results or the lack of duality, and here's one of such results. So here instead of previously when I described the singularity structure, we take epsilon equal to 0, right? That's a sort of asymptotic result if you wish. But this is precise, this is identity. So let's see, we got 1, 2, 3 relative entropy here. We got the other two quantities. So I want to spend a few minutes discussing this equality. Okay, so I want to explain what these quantities are. So these three are relative entropies, and omega is the vacuum states, and omega J1 tensor omega J2. These are the tensor states where we have I1 union with I2. This I is the interval on the circle. It's a disjoint union of two intervals. So its complement, I prime is the complement. It's also a disjoint union of two intervals. Okay, so these are the two relative entropies. C is the central charge. Eta here is the cross ratio associated with this interval. And let's look at the right-hand side. So what is this? Omega is the vacuum state, and Fi here. Fi is the conditional expectation from this larger algebra into the smaller algebra. Okay. Notice that because I1, I2, J1, J2 are disjoint, this observer algebra is contained in the commutant here. So we have a larger algebra, and Fi is the in this case the unique conditional expectation. Okay. So when you compose omega with this unique conditional expectation, that's not a state, but this is state on this bigger algebra now. So my omega is also the vacuum state restricted to this bigger algebra, and this is a relative entropy. Okay? So these three entropies here, relative entropy, are all entropies, relative entropies, but all three different algebras. Okay, and what is this term here? This is half log of mu a. Mu a is the global index, as before. This is index-like quantity. Okay, so this I claim is a very interesting quantity because the duality relation, which I didn't quite have time to describe, is actually a special case when the right-hand side is 0. Okay, so one can show that the right-hand side is 0 if and only if the mu a is equal to 1. Okay, so that's why in the free fermion case we see the duality, but in other many more interesting examples, when the mu index is not equal to 1, when the representation theory is non-trivial, you always have this non-zero term on the right-hand side. Okay, so this relation is very interesting because once again we play this game of monotonicity, right? This relative entropy is monotonic. And if you use this, you get inequality like this, and the result which is quite non-trivial. Okay. See, the thing is, so you might think that this maybe follows from the monotonicity here, but one of them is increasing, one of them is also increasing. So the fact that they satisfy this actual monotonic increasing is non-trivial. Okay. Anyway, so that's one result I want to talk about because it's the equality relating the relative entropy and index theory. I should also say that we proved this duality is also true for full two-dimensional CFT. Okay, And in that case, if you have duality relation, in other words, the right-hand side of the previous formula, this formula here, the right-hand side is 0, if and only if the global index is 1. Okay. I should mention that Cassini and others have called such a theory complete in their recent investigation of symmetries using operator algebraic language. Okay. All right. So yeah. So let me spend the last 2 minutes, maybe 3, discuss the proof and one of the things which come out of the proof. So the proof of such a relation is partially based on the following results. Okay. So so here's the setup. We got conditional expectations. The setup is so that all these terms make sense. We got 2 conditional expectations that can be composed. So on the left-hand side, I have relative entropy, and on the right-hand side, I have 2 relative entropy associated with these 2 conditional expectations. What I like about this formula is see how, this looks very simple, and looks like this relative entropy behaves additively and the composition of conditional expectations. Okay, so this is one of the key results behind the proof, and I should mention that this result, in the special case, the type 1 factors, this is equivalent to what Cassini and collaborators call the entropy certainty principle, and looks like they have done some interesting work motivated by various physics questions. Okay, but I should say this formula is more general than that. Okay, and I think there's still consequences to explore coming from this formula. Okay, okay, right. So this will be my last transparency. So so like I said, this formula here looks like this relative entropy behaves additively on the composition of conditional expectation. Okay, so that reminds us, some of us, a formula about logarithm of index. Index behaves multiplicatively, and if you take a logarithm, it will behaves additively. So this looks like that, and in fact, there are some relations there. One easily sees that this is always bounded by logarithm of index. Okay. And in the cases, especially this conformal net case, one can show that if you take this interval and if it goes to the circle, in other words, it's getting larger and larger, eventually, you approximate the whole circle, then this here, notice that it's going to increase, and it increase exactly logarithm of index b. Okay, so this seems to be more refined invariant. Okay. All right, so I think that's all I want to talk about. Thank you for your attention.
Thank you, Feng, for this beautiful and dense talk with many interesting results. Is there any question? Maybe I want to ask you a question about your last slides. Is there any higher dimensional version of your results? Feng?
Well, yes. Well, the last one, of course,
when you reach the logarithm of the index.
Yes.
There's a limit.
Yes. I think this is well, in this context, for the high dimension, I assume you mean the high dimensional quantum field theory.
Mm-hmm.
Well, in that case, as you might know, this quantity is just a logarithm of some integer. So it's possible. Yeah, I think I haven't thought about this, but I think it's possible. But of course, the the value of the index might not that be interesting. So that's also the reason I restricted the chiral case, where you know that the index takes much interesting values.
I think Henning Rehren is raising an hand.
Yeah, hi Feng, nice talk, very quick. But one is often interested in area laws, especially in higher dimensional quantum field theory. Well, in the chiral theory, there is not much of an area or surface. It could just be the number of boundary points which plays the role of an area. Is there some area law, say, if you increase the number of intervals, that something increases with the number of endpoints?
That's a good question. As far as I know, I mean, there are some results in the case of in the case of lattice approximations and maybe what they call the quasi-classical approximations. But as far as I know, there's no results in the continuum limit in the high dimensional case. I mean, there of course results computations using replica trick by physicists, but I don't know how to justify that in a high dimensional case. No, as far as I know, maybe I'm wrong, but I don't know any mathematical results in that direction.
Thank you.
There is a question in chat by Stefan Hollands. He's asking whether the analogous result on mutual information in 1+1 CFT that are not simply products of chiral ones.
Can you repeat that question again, Roberto? I can't.
If you have analogs of your results in 1+1 dimensional conformal field theory, in the case the conformal field theory is not just a product of two chirals.
Yes. In my paper, I also discussed the case where you have the full theory in the CFD case. Of course, the full theory always contains a subnet, which is the tensor product, of the restriction to the light cone. And yes, there is a result in that. Yeah, I think it's the last section of my paper on global index and the relative entropy.
Is there any further question? Well, there was so many results that we should think of it. So if there is no further question, I would thanks again Feng for this beautiful talk, and goodbye to everybody.
Okay. Thank you.
There is a talk. No, this is a class. Okay.
Thank you. Thank you very much. Bye-bye, everybody.
Bye.
Goodbye.